All right, we got 5 minutes to go. If you're watching the live stream, just remember that I can read Discord on the side. You can also subscribe to the voice part of Discord, um, but only listen to one or the other because the part on Discord is more real time. So it can be confusing if you're listening to both at the same time. All right, we got 5 more minutes ish, four, maybe three. All right, we got 10 seconds before we start the lecture. All right, it is officially noontime and I am starting the lecture now. I hope you guys are watching the screen part and while having an eye on the Discord part, because the Discord part is how I can get that you guys have a question. You can ping me, just so that I know that you have a question. So without any other overhead, we're gonna start the lecture just like usual. Okay. So let's go back and review, what we have talked about up to this point. Okay. Okay, I'm gonna pull my mouse pad here, kind of as a quick, whiteboard. So what we have talked about up to this point are three things. Okay, maybe four. One is propositional logic or calculus, which is really more or less a mechanical system to derive well-formed formulae that are also known to be true from the ones that are known to be true to begin with that are inside the iota. So that's propositional logic. The second one that we talked about is CNF or conjunctive normal form. So conjunctive normal form is a very weird way of expressing Boolean expressions, because everything is expressed in the form of an overall conjunction, while at the same time, um, let's see, I'm keeping an eye on the Discord part, and it says for people too lazy, check Canvas. Okay, there we go. Okay, I'm assuming there's some conversation going on that I do not see entirely. All right, and I'm guessing someone needs to find the YouTube link. All right, there we go. And thank you, Alex, for pointing that out. Um, but I'm moving on with the lecture. Everything is being streamed and recorded, so that's the nice part about YouTube live stream is everything is recorded. Okay, so conjunctive normal form is a very weird, restrictive form of Boolean expression, but it is supposedly, okay, and we might test it out today, as expressive as the usual Boolean expression. So we'll take a look at that today. And then the third thing that we also talk about is resolution. So resolution is a way to combine two conjunctive normal forms expressions into one, and in the process of combining, it is concatenating the two while consuming, quote unquote, consuming the term where in one disjunctive term is negated and in the other disjunctive term is not negated. That's resolution. And then in the previous class, we also talked about proof by contradiction, which is a technique to prove something by negating the theorem to be proven first, and then we show that that is not possible. So if the negation of the theorem is not possible, then we'll go ahead to assume that the theorem has to be true. Okay, so these are the four things that we have talked about up to this point, and they are somewhat disjoint at this point. Before we move on any further, I am going to show that all the rules for converting a general expression into a CNF. So I'm going to go over most of the rules because you'll need that for the homework assignment. So this part is about converting Boolean expression to CNF. All right, there we go. So when you convert a general Boolean expression to CNF, there are a few things that are super handy. Okay, so each one is on its own a particular rule that you can use. The first one is if you have an expression x and x implies y, this is really the same thing as saying that not x or y. So in this notation, I'm going to use a plus to represent or, and multiplication to represent conjunction, because those are just a whole lot easier to type. So I'm not gonna use the bar or the ampersand here. Also, I'm going to use negation, use exclamation point for negation because I just borrowed that from C and C++. Okay, so this is the first rule. Okay, this is you can call it the definition of implication. There we go. The next one you kind of know already. X plus y is really the same thing as y plus x. It is commutative, because all it does is to change the order of the two, and disjunction does not care about the ordering. The next one you probably don't need it, but if you want to, xy, which is x times y, or in Boolean expression, it means x and y is the same as y and x. Okay, I'm just using this notation because that saves me from typing one single character for the multiplication. Okay, so these we kind of know already. So let's go into the ones that are less common. Okay, this one is the negation of x or y is really the same thing as not x and not y. That's one part of De Morgan's law. So this is De Morgan law. The other one is also De Morgan's law. It is the negation of x and y is really the same thing as not x or not y. This is also De Morgan's law. Okay. So the usefulness of De Morgan's law is it is distributing the negation which applies to and or into a negation that applies to whatever the and or is operating on. But at the same time, you have to remember the or is changed to an and right over here, and then the and over here is changed into or over here. So by distributing the negation into the inside of an and or, you also have to change the and or to the other one. Okay, and becomes or becomes and. Okay. The next one is distribution or distributive. So if we have x and y or z, this is really the same thing as x and y or x and z. So this one is nothing new to us because in arithmetics we have the same distribution law. The other one, this one looks kind of odd because we don't have this in normal arithmetics, which is x or x, y and z is the same thing as x or y and x or z. Okay. I know it looks kind of odd because we are not used to this one, but it does work. Okay. Let's see what else is helpful here. So using these two, you can actually do FOIL, because FOIL is just basically saying what if x itself is, let's say, a plus b, right? So if x is a plus b, then we have a plus b over here, we have a plus b over here, and then you reapply the distributive rule, and then you get FOIL. Okay. So these are some of the most important ones. The other ones are the identities, which helps to simplify stuff. So for simplification, anything or false is just that original anything. Anything and one, or true and whatever, is just whatever. And then we also have false and whatever is always false. And then x or true is always true. So these are really helpful for simplification purposes. Another one that's really good for simplification, there are two more that are good for simplification, is if you have a term x already, and and it is conjunct with x or something. Okay, so we'll say x or y. That really is the same thing. It always boils down to just x. In other words, in a conjunction, in an overall conjunction, the more restrictive term is the one that restricts the overall expression. On the other hand, if you have x or y, oops, let me take it back, x or x and y, So x is the more general term. So in this case, it is always just simplifying to x. Now, you don't have to take my words for this. You can use a truth table to prove every single one of these rules that are going to be helpful when you do your homework assignment. I think these are the only ones that I can think of. Let me just double check. Okay, so I'm going to pull the mouse pad on one side and look at my notes on the other side. So I know the notepad is out of your view at this point. So this part here, converts a normal Boolean expression into a CNF. So the way it works is if the overall operator is a OR, then we say psi is the OR of all the psi terms. Phi is the OR of all the psi terms. Let's see here. Yeah, so this one is not as complete as what I have shown here. So these should summarize all the tricks that we used in the example. Let me scroll down to the example so we can take a look at it. Yeah, we took a look at this in the previous class. So the first thing we did over here is to change the implication to the negation of the first one, or the second one non-negated. And then what we did was to take this negation that applies to the OR, apply De Morgan's law, and it becomes this. And then we do a simplification because not R is just R. Okay, we'll go ahead and put it over here as well. Not X is just X. You won't see it, but I'm gonna put it back into your view in just a little bit. And then from here down to here, it is distribution. So we are distributing, we're distributing this term over here, which has an OR, over this term over here. So that's how we end up with another AND with a P over here, and then borrow the term, the operator in the expression that is being distributed, and then we have the other term, which is and T here. So that's just distribution. Excuse me. So now we have a conjunction that has three terms, or another conjunction that also has three terms. So we end up with 9 terms using distribution, which is what happens here. And then we factor. We use factoring to combine some of the terms together. Oh, no, I take it back. We are not factoring. We do another distribution. This not P is outside of a gigantic AND operation, which is over here. So I'm distributing the negation of P over all the subterms in this big O conjunction. So that's how we end up with this entire thing. And of this entire thing, some terms are simplified to 1 because we have a term or the negation of itself. I'm writing it down here too. So if you have a term or itself, or the negation of itself, it is always true. And then if you have a term and the negation of itself, it is always going to be false. Okay, I'm writing all of this on the side, and when I'm done, I'm going to show you all of these things. And then over here, we use the simplification of, because we're using an AND over here, so anything that has an extra OR is useless. So what that means is, since we have not P or R, which is more restrictive than not P or R or not Q, that means this term here, the one that is more general, can now be removed because the more restrictive term is going to restrict the other one. And the same thing can be applied over here. So this term also disappears because inside this term is a not P or R. So the extra or not Q can now be removed. So they all simplify to just not P or R. And then we apply the same thing to not P or not Q, which is this term over here. Okay, so that's just by itself because this term basically goes away. because it's more general. Okay, so let me pull the mouse pad back into your view so we can talk about that a little bit. So in here, these are all the rules to help us convert from Boolean expression to CNF. Now the order of applying these rules is kind of tricky. Okay, depends on what you're doing, and obviously the simplification steps are always going to be applied as soon as possible. If you see something that can be simplified, apply that. Distribution is always useful because it can break up terms. So basically, that's it. Okay, I can copy and paste this later on, into Canvas so that you guys have a copy of this. All right. So, are there any questions about converting a Boolean expression into CNF? And we can refer to this as an example. More restrictive. Okay. So there's a question, if just in case anyone is not reading the Discord. So the question is, what is more restrictive? So in the case of a disjunction or, x plus y or x or y is more oops, it's less restrictive. So I just go the other way. X is more restrictive than x or y. But in the case of a conjunction, x and y is more restrictive than just x itself. In other words, we are talking about which one can be, if x is true, then x or y is also guaranteed to be true. If x and y is true, we also know that x has to be true. That's what I mean by more restrictive. So I hope that explanation works. I'm just going to wait 5 seconds to confirm that no one has any additional questions.
I actually have a question. I just tried to get my mic working for the past couple seconds. It
Okay.
has to do with the distribution,
Mm-hmm.
and it was the oh geez, there's a tunnel. Let me just see if I can just mute YouTube. That's better. So it was during distribution, and it was the step just before we started turning all those statements into true, just one. There was a I think it was a P, not P, and R, and there was a Q, R, and a T in there. It was literally the step just before we started simplifying to ones.
Okay, so I
Um,
think you're referring to 4 lines from the bottom. Is that correct?
yes.
Okay, so which term is in question?
Okay, so it's not in sight right now. We're gonna have to scroll right a bit.
Okay. Which term?
Okay, so the not P, not Q, not T.
Not P, not Q, not T.
Yeah, not P, or not Q or T. Yeah, I don't see a direct correlation of what happens next.
I don't see a not P or not Q or not T. I see a not P or not Q or T.
Yeah,
So
that's what I meant to say. Sorry.
okay, so T is not negated.
Yeah.
Okay, so it is simplified because of not P or not Q. So let me pick out which one is not P or not Q first, right here. See the term kind of in the middle? It is not P or not Q or not Q. See that term?
All right.
So that term simplifies to not P or not Q because not Q or not Q is just itself.
Okay.
And because this term is more restrictive compared to the term of not P or not Q or T,
Okay.
so the more general term goes away because the overall operator is an AND.
Okay. That
So
makes
the
sense.
more
Thank
general
you.
term goes
All right.
away the overall operator is and.
Righty. So you might want to turn off the speaker or use a headphone because otherwise I can listen to myself in with a slight delay, which is okay, but it can be confusing to some other people. There you go. Thank you. So I'm just adding, that one over here. X or X is just X, and then X and X is also just X. So they can be helpful in simplification as well. So are we good so far? I'm just going to wait 5 seconds and see if there are any additional questions. Okay, there does not seem to be any questions, because if I see anyone typing, it will show on Discord and nobody seems to. Oh, okay, Scott is typing. Oh, okay. Thank you, Scott, for confirming that there are no questions. Good. Excellent. All right, so now that we have more or less established that CNF can be used to express any Boolean expression, now we want to string everything together. In other words, we want to combine CNF, which is basically a weird but complete alternative of all Boolean expressions. Okay, so that's CNF. We want to combine that with resolution first. So the way we combine it with resolution is basically just to go back a little bit and look at resolution, which is right here. And the only part that we have to look at is this part here, because the rest is a proof that resolution works. So this is the only part. Can I mute myself on Discord? Yes. Okay. So I just answer a few questions regarding turning on or turning off mic on the other side. Okay. So let's get back to resolution. So the way resolution works is if you have two disjunctive terms and one has the negated version of one variable and the other one has the non-negative version of the same variable, then you can join them together. In other words, you can look at this psi and this not psi over here and just look at psi as one variable. And that gives us a mechanism to join the rest of the expressions. One has phi over here and the other one has rho over here, and we can join the rest into another disjunctive term that is basically the concatenation of phi and rho, and it becomes a disjunctive term. And the nice thing about this is if phi itself is a disjunctive term and rho itself is also a disjunctive term, then so is the or between those two disjunctive terms. So that means if this here, okay, if this part here is a disjunctive term that we can use that is well formed, and this term here is also well formed, it guarantees that the output is also well formed, which is really handy. Okay, so that's resolution. So why don't we do a little bit of exercise on resolution and see whether we have any questions about that. This is just proof by contradiction. Okay, I'm changing the order just a little bit here. We'll show proof by contradiction again. So proof by contradiction this time is going to be an abridged version, because we talked about this in detail last Wednesday. So the abridged version of proof by contradiction is really just to look at this part here, okay? Because the rest, once again, is to prove that this corollary is valid. Okay, so we will take this and go like, okay, what is it saying? It's basically saying if P implies Q is known to be true, then you can pick some random R so that P and R is always going to imply Q and R. It is guaranteed. Now, that by itself is kind of okay. That sounds kind of cool, but what does that have anything to do with proof by contradiction? So when we scroll down a little bit, okay, then we can start to see um, it is important to understand what is psi and what is phi in this context. So we have to go back to the paragraph before to understand what those things are. So in this case, what psi is a conjunction of everything in iota. But what is iota? What does iota mean? Iota is a set of well-formed formulae that are known to be true to begin with. In other words, don't ask me why, these things are just known to be true. Okay? So that means psi is representing everything, or the conjunction of everything that is known to be true from iota. Okay? Well, how is that going to help us? Well, this is where we start. What is phi? Phi is the theorem that we're attempting to prove. In other words, we don't know whether phi is can be implied by psi or not. But if it can, then phi is a theorem from in this particular system. In other words, if phi is really a theorem, then this implication is true. Okay? So as long as phi is a theorem, psi implies phi, it's going to be true. So now we say, well, what is that going to help us? Well, now we apply the corollary that we proved a little bit earlier, which is basically saying, well, if we know that phi implies psi, no, the other way around. If we know that psi implies phi, then we can introduce a random term of some kind so that the conjunction of psi and that random term and the conjunction of phi and that term, those two one would still imply the other one, once we introduce the conjunction with that random term. So in this case, it's not so random. We choose the extra term to be the negation of phi, but it doesn't matter because it should still be true. In other words, what we know should still be true. So that means when we combine these two, it becomes phi and psi, excuse me, okay, it becomes psi and not phi, which is from the left-hand side of the implication. That's fine. That part is not very interesting. But the other part is interesting because this part is basically saying this is phi and not phi. But phi and not phi always simplifies to false. So that means if phi is indeed a theorem of the entire propositional system, then if we combine the negated proposed theorem and everything that is known to be true, then it is going to imply false. And this implication is going to be true. So now we have to ask, how can this implication be true when the right-hand side of the implication is already false? Well, you guessed right. Okay, from the truth table, the only way that this implication can still be true is phi and not psi. No, yeah, well, okay, it's the same thing. So psi and not phi has to be false itself. Okay, so that's the bottom line. Okay, we want the conjunction of everything that is known to be true and the negated theorem to be false, because that's the only time we can show that this implication is true. So I'm not really sure whether you guys are getting this or not, but we can go ahead and take a look at the Pigeonhole Principle, which seemingly has nothing to do with this. So I'm going to open a new tab, and it opens up Wikipedia. This is the Pigeonhole Principle. So in the Pigeonhole Principle, it says that if there are more items that we have to put into containers, in other words, there are more things than there are containers, then one container must have more than one items. Okay. Well, that seems to make a lot of sense, right? I mean, why would we want to have to prove something like this that seems to just be intuitively correct? Well, because if it is intuitively correct, we cannot just say it is by intuition that this is true. Okay, it still needs to be proven. So we'll go ahead and prove this, and I'm going to use my text editor for this purpose. We can actually do it this way. So let's go ahead and prove the pigeonhole principle. Okay, proof of the pigeonhole principle. Okay, so there are n pigeons and m holes. Okay, and it is given that n is greater than m. Okay, the theorem is to say at least one hole has more than one pigeons. That's basically what the theorem is saying. In other words, these are given. Okay, there are n pigeons and m holes, and m is greater than n is greater than m. That is given to us. Okay, so this is not what we are going to negate. What we're negating is going to be the proposed theorem, which is saying at least one pigeonhole has more than one pigeons. Okay, so let's see what it means when we say at least one hole has more than one pigeons. Okay, so let's see if this works. Okay, if I say it is not the case that at least one hole has more than one pigeons, what is the equivalent way of saying this in this case? Well, we can. This is the part where live streaming doesn't work as well as having an actual live class. It becomes a little bit cumbersome for you guys to answer the question. I can turn on the voice, which helps a lot, but that also leads to confusion because the video recording is 5 seconds behind the actual live session in Discord. Okay. So there's a question. Is one requirement here that all m hold at least one n? Nope, that is not the case. So just kind of imagine that you have n pigeons and m holes. The question is if all the pigeons are to return home and has to go to one hole, do we have at least one hole that has more than one pigeons? That's the question. I'm not sure whether that is answering the question or not. I can give you a kind of text example here. So let's say we got 5 pigeons, right? 1, 2, 3, 4, 5. Okay. So there are 5 pigeons, and then there are 4 homes for the pigeons to return to. So the theorem says that at least one of the homes or holes will have more than one pigeons. That's what the theorem is saying. So Kevin is typing. I'm gonna wait for his text to show on Discord. And then Bu is typing too, so I'm gonna wait a little bit. Okay, so good now. And what about the other one? Let's check. So it's possible for 4 pigeons to stuff themselves in a hole with 3 empty holes. Yes, I don't really care because the theorem says at least one hole has more than one pigeons. That's the only conclusion that I'm guaranteed. So we can have 2 pigeons in one hole and then 1 pigeon in the other 3 holes. Okay, or we can have all pigeons, 5 pigeons in one single hole and then the other 3 holes with no pigeons. So is that okay? Okay, nobody's typing. I'm going to assume it's good. Okay, so let's go back to here. Okay, so what does it mean when I say I negate the theorem? Well, if I negate the theorem, all I am saying is this is false. Okay, it is not true that at least one hole has more than one pigeons. But what is another way to say this? The other way to say this is to say all holes has at most one pigeon. Okay, so I want to let you guys look at this a little bit and kind of let it soak in. Okay, does that make sense? It is not the case that at least one pigeonhole, when one hole has more than one pigeons, is saying the same that all holes have at the most one pigeon. Now we can do this using what we already learned about quantifiers. Okay, so if anyone wants to know how to do this using quantifiers, I can actually use that as well. Okay, we don't have any questions here. All right, so let's just say that this is the case. Okay, so now we can say that the negated theorem is to say all holes have at most one pigeon. Okay, now how is that going to cause a contradiction? Well, if all holes have at the most one pigeon, that means the total number of, but this means the number of pigeons is no more than the number of holes. Does that make sense? Because every single hole has at the most one pigeon, and we only got m of those. So that means this alone is basically saying m is less than or equal to, nope, it's saying n is less than or equal to m. The number of pigeons is the number of pigeons, which is n, is less than or equal to the number of holes, because we say that all holes have at the most one pigeon. But then n is greater than m and n is less than or equal to m leads to false. That's our contradiction right there. So let me just pause a little bit and make sure everybody understand how we got to the contradiction. There we go. So this is the entire proof, because I have to make it clear that the negated theorem combined with what is known to be true is leading to a contradiction, and as a result the theorem must be true. So I want to know whether this is okay or not before we move on. Alright, looks like there are no questions. Okay, so if there are no questions here, does anyone want to look at another example of proof by contradiction that has nothing to do with propositional logic? So I'm just going to wait for a few seconds here. Alright, so we got a few people saying yes. Excellent. Alright, so the next one is like this. Okay, so we basically say A, B, C are non-negative integers. Okay, so they're basically natural numbers. Look at those as natural numbers. Maybe we just rename those as natural numbers. Okay, it is known. Okay, in other words, this is given to you. Don't ask me why. Okay, C is the product of A times B. Okay, so that's given. So we got A as a natural number, B as a natural number, and C is the product of those two natural numbers. Okay. Then we know that A is less than or equal to the square root of C, or b is less than or equal to the square root of c. And this is our theorem. Okay, so let's take a look at this part here and see if we have any questions about what is given to be true and what the theorem is trying to say. So what is given to us is we have three natural numbers, a, b, and c. It is also given to us that c is the product of a and b. So that's given to us. Don't ask me why, but that's what you're given with. The theorem, or what we want to prove, is between a and b, one of them, or at least one of them, has to be less than or equal to the square root of c. So let's go ahead and take a look at some examples. Okay, so we'll go ahead and look at some known examples. Okay, so 35 is 5 times 7. Okay, we know that. And in this case, 5 is less than the square root of 35. Well, we just need less than or equal to, okay, but it still works. Okay, even though 7 is not, but 5 is less than or equal to the square root of 35. Let's move on to 36. So in the case of 36, we have 6 times 6, but guess what? 6 itself is less than or equal to the square root of 36, and this time it applies to both a and b, because a and b are the same in this case. We're talking about c as a square of a or b. All right, so let's take a look at a prime number. Okay, how does this work out with a prime number? 17. Okay, so 17 as a natural number is 1 times 17. Well, that's pretty easy, because 1 as one of the two numbers, is less than or equal to the square root of 17. Now, just because we can keep doing this all day long, right? I mean, with 36, we can re-express it as 3 times 12. And in this case, 3 is less than or equal to the square root of 36. So we can do this all day long and say, well, that seems to be true. Well, just because it seems to be true doesn't mean that it is always true. It is always possible that we have only tested the cases where the theorem seems to be true, but it really is not a theorem. In other words, it is not implied by c equals to a times b, and they're all natural numbers. So how do we prove this one? Okay, it seems to make sense, but how do we prove it? So the way to prove this is, once again, use proof by contradiction. So in proof by contradiction, we have to start with the negated theorem. So in this case, the negated theorem is to say it is not the case that a is less than or equal to the square root of c. So I'm going to rewrite this a little bit. A times a is less than or equal to c, or, okay, which is a plus. B times b is less than or equal to c. Okay, so that becomes our negated theorem, which is really just taking what we have here as the theorem and then just apply a negation in front of it. Just remember, in this case, the plus is actually a or, but instead of typing bar bar, I'm using just a plus. So, okay, if this is the negated theorem, why is it so bad? Okay, well, the first thing we do is to look at this in a slightly different angle. So we say, well, let's see what this looks like if we apply the distribute the negation, over the disjunction. In other words, we apply De Morgan's law. So it's the same thing as, okay, the negation of a times a is less than or equal to c, and the negation of b times b is less than or equal to c. In other words, I take this negation and I distribute it to the terms that we are originally ORing, which is this one and also this one. But in doing so, we also have to change the OR into an AND, because that's what De Morgan's law do. Okay. Now that we have this, now that we have applied De Morgan's law, we look at this and go like, I think there's a better way to say this. Okay, that means a times a, if it's not less than or equal to c, doesn't that mean the same thing as greater than c? Okay, and b times b is also greater than c. So are we good so far? do we have any questions about the negated theorem and how we can rewrite the negated theorem in a different way, just using Boolean algebra and normal algebra a little bit here? Okay, sounds like we don't have a question, so we're gonna move on. Okay, so what does that mean? Well, since we know that A, B, and C are all natural numbers, so now we can say that, hey, but this means that A times A, which is this portion here, times B, which is this portion here, is going to be greater than C times C. Does that make sense to you? Because this alone is already, okay, let me highlight which part. Because this alone is already greater than this, and then this alone, oops, is already greater than that. And since nothing is negative, then we can conclude that if we take this and then we take this, then the product of those two have to be greater than the product of this C and this C over here, which is now C times C. So I want to pause a little bit here and make sure everybody is okay with this part here. All right. Okay, nobody is typing and nobody seems to have any questions. So if you do have any questions, and I did not leave enough of a window to let you ask questions, just let me know by texting, and that's going to be good. Somebody PM me. Okay, that's about syncing stuff. Okay, well, we'll deal with that problem later. I can think of several solutions. All right, so getting back here to this part here. So is that really so bad? Well, it is actually really bad. Okay, so I'm gonna use normal algebra here. So in normal algebra, we'll have A times B times A times B. Okay, does that make sense? Well, this is just by reordering stuff in a multiplication, which is coming from a commutative law of algebra. And also we are just adding parentheses, which is coming from the associative law of multiplication. So I think everybody can accept that this product here, which has two A's and two B's, really is the same thing as A times B times A times B. Okay? Alright, I think most people can see where the problem is coming now. Okay, so this is a very typical algebra, manipulation. But then we also use what is given to us to be true, which is, guess what? C is A times B. So now we have C to replace this A times B. And this is also A times B, which is another C. So now we have C times C is greater than C times C. And that cannot be good, right? Because that has to be false. A natural number cannot be greater than itself. And therefore we have our contradiction. So let me just pause a little bit here. I'll pause about 10 seconds so that people have a chance to ask questions about this proof. Alright, 10 seconds have passed and I'm not seeing any questions. So either I have lost everybody, or there's a technical difficulty of some kind, or there's no question. Okay, excellent. So now we can say, because the negated theorem leads to a contradiction, the theorem is implied by what is known to be true. In other words, the theorem is really a theorem in this case. And then Carol says, it seems like this requires some mental gymnastics sometimes. Yes and no. So the thing about this is, to apply proof by contradiction, you first have to be convinced that proof by contradiction as a mechanism makes sense. Okay, so let me go back to my browser. Okay, where's my browser? There we go. Okay, so to convince yourself that this works, the first thing is to kind of reread section 5.4 and make sure that we understand that in section 5.4, first of all, the corollary makes sense, okay? Which means if we start with an expression like that, that expression turns out to be always true. And that means, it doesn't matter what you pick as your P, as your Q, and as your R. It doesn't matter whether P is true or false, doesn't matter whether Q is true or false, doesn't matter whether R is true or false. It is always true. Okay, this expression here is always true. Now, for those of you who want to go through everything and say, okay, can you prove this using a truth table? Okay, the answer is yeah. This can be proved. This can be proven using the proof by using a truth table. So all you need is to have a truth table that has 8 rows, because we have 3 independent variables, and then you just work out how P, Q, and R can be true and false in different rows, and then you work out this particular expression, work out the value of this particular expression, and you will find that it is always true. So that is what we are talking about, is this is always true. But what is always true? What is always true applies to the last operator, which is this implication. That implication is always true. So that means if P implies Q is true, then this has to be true too. Okay? So you just have to accept that this is a corollary, which proves that this implication is always true. Then we work out and say, okay, what is a normal theorem proving process? We start with everything that is known to be true, and we say somehow that implies the theorem is also true. That is a proof, a direct proof. But instead of doing it this way, we're going to say, well, let's combine it with the negation of the theorem using a conjunction. Now, why can we do this? It's because of the corollary that we just talked about earlier. But when you do that, we end up with everything that is known to be true, which is this part here, and the negated theorem is going to imply false. But we already know that this implication is going to be true, as if this implication is true, then this implication has got to be true too. But in order for this implication to be true, that means this part has to be false. So that means if this is false, then this implication is true. But when this implication is true, it goes back to prove that this implication is true. And as a result, we have the proof to show that whatever is known to be true to begin with is implying the theorem. So I'm hoping this helps to answer the question of proof by contradiction itself. Are we good so far? Alright, looks like we are good so far. So now we're going to move on to an example. Okay, so we are not going to go through all the individual steps, okay, because we already got this proven a little bit earlier. Okay, it derives into this particular psi, and what we want to know is whether this phi is a theorem or not. Okay, so what we'll do is we are going to I'm going to use mousepad here. Okay, and we can do some derivation. Well, actually, we don't need the I don't need the mousepad in this case. Let me just hide mousepad again. So in this case, this is what we know to be true. Okay, this is known to be true. This is in iota. Okay, so if this thing is in iota, that means after we derive everything, that means this it's also in this is also it's known to be true, and this is also known to be true. Both of these are well-formed formulae, in the case of we want to use CNF. Okay, so psi is given, and phi, which is this thing here, is, well, do we know whether psi is going to imply phi? That's what that's what we want to find out. So phi is representing the theorem that we want to prove. But in order to prove the theorem using proof by contradiction, we are going to negate it first. So we have to work with the negation of phi, which is the negation of not t implies p. And then we use the definition of implication, negating the first part, which ends up with a double negation, or the second part. And then we apply De Morgan's law, which is the negation of an or becomes the negation of the components of the or, but changing the disjunction into a conjunction. So now we end up with this. So now the question is, well, does that look like a CNF to you? It does look like a CNF because this is a very simple disjunctive term. It doesn't look like a disjunction, but it is a disjunction with nothing, or it's a disjunctive term with only one single term inside. And same with this one. Now, because this is a conjunction of two disjunctive terms, this by itself is a CNF. It is a conjunctive normal form. When you concatenate two CNFs, the resulting CNF is always a CNF itself. So now, when we take a look at, okay, tell me what is psi. Psi was like this, but then we transformed it like this last Wednesday. So that is psi over here. What about the negation of the theorem not phi? Well, we just did the derivation, which is here. They're both CNFs, so as a result, when you combine those two using a conjunction, the resulting term is also a CNF. So, but wait, hold on a second here, okay? Because if phi is actually a theorem, that means this whole thing will reduce to a false at some point because it is the conjunction of what is known to be true as well as the negated theorem. Okay. So now we take a look at this and say, well, what do we do about this? Can we resolve anything here? So the way we resolve, remember, is to take a look between any two disjunctive terms, okay, like this one versus this one, and then we ask the question, do we have a common variable where it is negated on one side but not negated on the other side? The answer is nope, we don't have it between these two because not p, well, we need the other one to have a non-negated p. Nope, none of these has a non-negated p. What about r? Well, we need the other one to have a negated r in this case. None of these has a negated r. Okay, so if the first disjunctive term cannot be resolved with anything else, let's look at the second disjunctive term and see if we can resolve with anything that is after it. Okay, so once again, we look at not p. Nobody has a non-negated p over here, so it cannot be resolved. We look at the negation of q, and nobody has a non-negated version of q, so it cannot be resolved. Then we look at this one and look at all the terms after that. Does anyone have a non-negated t? Nope. And then we have the last term left. When you look at the last term by itself, it always cannot be resolved because there's nothing else that it can resolve with at that point. So now we have shown that, hey, when we get to this CNF, resolution doesn't work at all. There's nothing to resolve with. Well, that means phi in this case is not a theorem because we cannot arrive at a contradiction. Okay, so in this case, phi is not a theorem. So now we want to look at another one, another example. What if we look at phi prime this time? And phi prime is a slightly different Boolean expression. Is that a theorem from the original psi that we have talked about? So to know whether it is the case or not, we're going to negate the proposed theorem. So we are negating the implication. We first use the definition of the implication, and then we use the Morgan's law because we have a negation applied to a disjunction. Then we apply the negation to each individual term in the original disjunction, and then we change the disjunction into a conjunction. There you go. And then we do the simplification. The double negation is cancelled out. Double negation is cancelled out. So we just end up with P and Q in this case. So now we combine everything that is known to be true, which we know as psi, and the negated theorem, which we know as the negation of phi prime. So we are just taking, psi, which is this part here, and not psi prime, not phi prime, which is this part here, and we combine those two together using a conjunction. So let's see if this time we got anything that can resolve. Okay, there are a few things that can be resolved. I decided not to resolve this term, which has a negative version of p, and this term, which has a non-negative version of p, because I wanted to get to the answer as quickly as possible. But if you want to resolve these two, it's fine. Okay, it will produce a term with r by itself, which is fine. It doesn't hurt anything, but it doesn't lead to a contradiction eventually. So what I did instead was to look at the second term. Okay, so look at the second term. It has got a negated p, and look at the third term, which is the non-negated p. So when these two terms resolve, okay, they go like, so what is it, so this thing has nothing to contribute. So it basically, after the resolution, it becomes an empty string, so to speak. So we basically, the result of the resolution is just the negation of q itself. This is the result of using this term and this term here as in resolution. So do we have any questions about this part? How I chose two disjunctive terms to resolve and end up with a new term in the system. I'm gonna wait about 10 seconds here.
So how exactly do you only have a negated q after that resolution?
Okay, so the question is, how do I end up with the negation of q after the resolution? So let me just kind of copy this on my mousepad, and then I'll write it out in the mousepad. So we have not p or r, and not p or not q, and we have p, and then we have q. Okay, there we go. Okay, I'm gonna pull up the mousepad over the, oops, that's not what I wanted. There we go. So let me just kind of put this right next to the window first, and then I'll explain why that is the case. So is this part okay? I am really just copying the first line, which is here, in the more easily typed format over here. We don't have any questions there? All right.
All right, makes sense.
All right, so now we go here, and then we ask, can we say that this is the same thing as, I'm just copying the first view here. Then we look at P and go like, well, that doesn't look like a disjunctive term to me. Let's make it a disjunctive term. And we look at Q and go like, that doesn't look like a disjunctive term. Let's make it a disjunctive term. Are we buying this? Because anything or false is just that anything itself. that okay? Are we good?
Okay, that makes sense.
Okay, so if that makes sense, then we can now say, hey, okay, let me refocus here. So when we look at this particular disjunctive term, it certainly has the negative version of p, and when we look at this disjunctive term here, it certainly has the non-negative version of p, so they can resolve, right? So when they resolve, it means p, not p, will go away because they quote unquote cancel out, and then the leftover of these two disjunctive terms is going to be not q from here, and it's going to be false from the other one. So that means as a result of this resolution, now when you apply resolution, whatever is known to be true at this point remains to be true. So that part is just copied. And then the new term, which is the result of the resolution, is ANDed with the rest. So basically the CNF gets longer and longer. So now we say, okay, let's combine these two terms, but P, not P goes away. So we concatenate the rest. So we have not Q or false. Is that okay?
All right.
Okay, so if that is okay, then we'll say, can we resolve any more? Oh, yes, we can. Look at this one. It has got the non-negative version of Q, and then look at this one. It has got the negative version of Q. So these two disjunctive terms share a variable where it is negated on one side and is not negated on the other side. So let's go ahead and combine these two. Well, when we say combine, it means let's concatenate the rest of each disjunctive term. The rest of this one is just false over here. The rest of this one is just this false over here. So when those two resolve, okay, I'm just going to be super lazy and just copy and paste here. So when those two resolve, we have false or false. The first one comes from here. The second one comes from here. We're concatenating false, false to becomes false or false. Is that okay? Are we good?
Yes.
Okay. So now we look at this and go like, now we apply a simplification because false or false is just false. Are we still okay?
Yeah.
Okay. Now, because this false is in a large conjunction, it is ANDed with a whole bunch of stuff over here. But in a conjunction, if you have at least one term of the conjunction being false, the entire conjunction is false. Are we good so far?
Yes.
So, once again, so now we know that when we have this part here is our psi, which is what is known to be true. This part here is the negated version of phi prime, which is the negated theorem. So when the what is known to be true is ANDed with the negated theorem, we end up with a false. That is what we want to get improved by contradiction. This means that the theorem is actually a theorem. It is implied by what is known to be true. Are we good with this? Because we just combined all of those concepts that we have already introduced in this exercise.
All good.
All good. Okay, excellent.
Oh, never mind.
And this is it. This is the entire thing. Forget about this symbol over here. That's just me playing with LaTeX to come up with the icon on the Discord channel. It spells TAK, by the way. The T is the transformation rule, and then the A is the for all, and then over the funny looking K. So if this is good, okay, I'm going to release the homework assignment. So let me go to the homework assignment here. It's called CNF, and let me go ahead and change the due date. Oh, we got one question down here. Okay, it's actually a few questions. So one question is, does that mean the not Q and Q will cancel too? Yes. They cancel out to become false if there's nothing left. And so phi prime is true by contradiction. Phi prime is not true by contradiction. Phi prime is proven as a theorem by proof by contradiction. So as I work on this part here, I'll give the class a little bit of time to think about it. Today is the 16th, so plus 7 is the 23rd. Oh, okay. I don't want to make this due in 2012. That may not work. There we go. All right, save. Oh, okay, here's another question. What happened to the R? Okay, let me put this back here. All right. The R is still here. Okay, so we still have these terms over here. So if I did not go for the most optimal way to prove this, I could have done this using made the R by itself. In other words, I look at this disjunctive term and ask, okay, we have a not P over here. We look at this term here and say it has a non-negated version of P over here. So these two can resolve. So when those two resolve, okay, so let me just kind of derive it over here. Then we concatenate what is left over from this one after not P is gone, and we concatenate what is left over here after P is gone. So that means we have R or false to begin with. So with all the extra steps here, you could keep that R or false or just R itself. It just doesn't help in the proof itself. In other words, this is one extra step. It is not wrong, but it doesn't help to get to where we want to go. But it doesn't hurt either. So I hope that addresses the question of what happened to R.
All right, so I do actually have one more question. Why do we concatenate instead of just simplifying?
Why do we, okay, so there's a question which is, why do we concatenate instead of simplifying? We do the concatenation because the application of resolution is the only transformation rule that we have left. So we do everything
Okay.
by resolution. We just need to somehow get to a false at the very end, or we get to a place where we cannot resolve anymore. So if we get to the point where we cannot resolve anymore, but nothing resolved to false, that means the theorem is the proposed theorem is not really a theorem. But if we get to false, that means the proposed theorem is in fact a theorem.
All right.
All right. All right, so let's talk about the homework assignment. Sorry about the bumping of the mic. Let's talk about the homework assignment a little bit. So this is your homework assignment, and I want you to convert this into a single CNF. So this homework assignment has nothing to do with resolution. Do not resolve, okay? You might find all the transformation rules that I have talked about today to be helpful. So I'm just going to, I will copy and paste this part here into Canvas just so that you guys have this stuff to begin with. So here's Control C, and I'll paste it, somewhere a little bit later on. But this is your homework. This is your homework assignment, and you can use the same symbols that I'm using. Using exclamation point for negation, multiplication for and, plus for disjunction. That makes it a whole lot easier to type your answer. And let me go back to the main page, and I'm just going to paste all the transformation rules into one spot so you guys can get to it more easily. So I'm just going to add a page. It's going to be a new one, and we'll say Boolean algebra. You cannot see it yet. Once I publish, you'll be able to see it. Okay, and then just paste what I had earlier, and then I can save and publish. There you go. So now when you attempt to do your homework, you have access to all the Boolean algebra transformations that I just mentioned in today's lecture, which is here in Boolean algebra. Alright, so I think we are coming pretty close to running out of time. So next time we are going to start with discrete probability. So you might want to kind of look at counting, which is a note that I typed, and we can do a preview over here. So this is what I want you guys to read at least a little bit before Wednesday, is to get familiarized with some of these terms. And I know some of these symbols look kind of awful, so just focus on the concepts, and instead of the actual detail. We'll talk about the details during class on Wednesday. So before I stop today's streaming, are there any questions? I'm gonna wait, let's say 20 seconds or so. I swear I can hear crickets. Alright, apparently there are no questions. Alright, so I'm going to hold my office hour. Oh, okay, somebody is typing. Let me just wait for that. 2 people are typing. Excellent. Okay, first question is, did I post last Wednesday's lecture? And the answer is no, I probably forgot, and I'll go ahead and post that one. So that's 1 week ago, less than 1 week ago, 4 days ago. Another comment on Discord is, when asking a question, do you want us to type it in or ask? I can do both. So basically, I turn off my mic in Discord, so the only way you can hear me talking is through YouTube, so there's a little bit of a lag. But you can use voice in Discord to ask questions. All right. Okay, well, you guys are welcome. I'm glad this kind of works out for all of us. And I'll start to look into, perhaps streaming using Discord, because I know Discord has a very low lag when it comes to streaming, but it doesn't record. That's kind of the problem. So I want to combine, what YouTube is good at, which is, recording, and also closed captioning, and also Discord, which is kind of a lot more live. We have to practice not to talk over each other. I don't hear anyone talking over each other. But there is definitely a lag in the process, so that part can be a little bit confusing. Discord doesn't have lag when it live streams, so that's a possibility. But as I said, it doesn't record, so I can combine the two. I can do both YouTube and Discord. So YouTube is good for reviewing later on, and then Discord is good for live. So I think we can do it that way. Hahaha. Exam 1, not yet, but since I'm now home and have more time to work on this kind of stuff, it'll be done relatively soon. And then Victoria is typing too. Okay, Victoria wants an ungraded assignment. Or is there a good resource I recommend for practice problems on this module? That is a great idea. Let me see. So I can give you guys some smaller expressions to convert to CNF, and I will disclose the answer on Wednesday. So this way you guys get a little bit of smaller things to work on instead of working on the big thing that is going to be a little bit. It will be a little challenging, but you just have to kind of keep good track of what is going on when you do that conversion. So yes, I will give you an ungraded assignment, and we'll talk about it on Wednesday. All right. So I think the lecture portion is done. I'm going to stop streaming, but I will leave Discord up at least for another half hour or so. So this way I can kind of keep track of the conversation over there. So streaming is going to close now.